anybody else waiting for? Okay, so I think we should start. So today is, I guess, a truly historic thesis defense. It's sort of the mark of a thesis defense is how many important people show up for a defense. So I can tell you, right, knowing the history, I think very, very, very many important people have showed up today. So I don't know how many of you know David? You know Dr. Goodman? Right? So we're all here, I guess, because of him, right?
Yeah.
Because he, and how many of you know Sudhir? So he was PhD number 3. Winla PhD number 3, right? And Fang Chen,
I'm number.
I don't know what number you were, but it's probably in the single digits, right? So anyway, Zhuyu is here. And when I joined WinLab in '94, he was already a grad student here. So he predates me in terms of seniority at WinLab. And I guess he did a master's thesis with Professor Rose. And then he was working with Dr. Goodman. And then Dr. Goodman subsequently moved on. And so did Zhuyu. Then decided to come back and sort of put the final chapter in what has been I would say focusing on positives. I guess the perseverance of really commendable, but I don't recommend it for the other people in this room. But anyway, so let's hear what he has to say about power control and packet switch networks. Okay.
Thanks, Dr. Mendel. First of all, I would like to thank my former advisor, Dr. Goodman, and my advisor, Dr. Mendel, for really for so many years for continuous encouragement and support. Many times I kind of at the point of giving up, but with their support, and finally I didn't do that and continue to come to this final stage. Thanks very much for your support and for your guidance to let me to this point. Okay, let's turn to the topic. So the title is about the utility-based power control for packet-switched wireless networks. So there's two things here. One is utility-based, which is some kind of microeconomics concept, and another thing is about the packet-switched network, and so these two things are combined together to do the power control. Okay, so some key points about this research work. So first thing is this is about the uplink power control for mobile to base station, and also it's for the interference limited wireless networks. As I mentioned already, packet switch data services, so that has burst traffic. And also in this research, we introduced quality of service parameter, which is average packet delay requirement in problem formulation. And also we use a concept of expected utility with units of bits per joule as a performance matrix. And the problem formulation is it's a game formulation. It's a non-cooperative game formulation. And we study the problem analytically based on a number of approximation methods, techniques, to reduce the problem to be something tractable. And also we also did the simulation studies on the problem and to see how the analysis and the simulation how they support each other. And also finally we have built a couple of idealized slot, we call slot by slot power control benchmarks, so we can compare what we have, what we proposed, to those idealized schemes to see where the performance is. outline. So about 9 sections. So introduction, and second one is just utility modeling for the packet switch system. And the third section is about what kind of approximation approaches we're using to analysis of to analyze the interference and packet success rate. And section 4, we discuss the formulation of the problem and the solution of the problem. And the fifth section will discuss about some characteristics of the power control strategy. And number 6 will discuss the simulation study results. And the 7 will extend the results to multi-class, multi-type traffic scenario. And number 8 will do some performance analysis. And 9, the last one just conclude. So introduction and overview. So first is the value of communication for wireless users. So what we look at the value of the communication for wireless users is from a performance perspective and from a cost perspective. So in this research, we look at the performance as the information throughput. Also, we call it as a goodput. So it's the useful throughput going through the channel for the user. And as a cost perspective, we look at the consumption of the battery energy of a mobile terminal because that's the only energy source available to a mobile terminal. So we burn that energy to try to get as much as possible the throughput information throughput. So that's two aspects of the problem. And generally for radio resource management for wireless networks, radio resources that have many things. You have a spectrum, which is also very limited, very expensive. You have bandwidth, you have transmit powers, and transmission rates, channels, base stations. You get to how to assign them, how to allocate them to obtain a maximum performance for the wireless networks. So as I mentioned before, we're focused on the individual wireless user. So it's uplink transmit power control problem. And for radio resource management, it's different type of traffic that has different ways to do the management. For example, voice versus data is very different because their requirement is different. Delay requirement is different. The packet average is different. And also, the approach we're using is called the microeconomics approach, which is in microeconomics we call some kind of utility maximization. So utility is something kind of preference of the user. The user want to maximize to get more and more. So this is an approach we borrowed from microeconomics to use in a power control study. So in wireless systems, users all compete for the limited resources in the system, try to maximize their own utilities. So this is distributed strategy because different users are doing their own things, make their own decisions. So this is best modeled by the non-cooperative game. This is some background. Okay, specifically for the utility-based power control for wireless data, this research actually originated right here at WinLab. So started with 1998, the first paper, and utility-based power control using the microeconomics approach by Dr. Udman, Dr. Nandan, and Baruch Shah, first paper. So after that, there's extensive research on utility-based power control we call circuit switched wireless data networks. We call circuit switch because we assume it's a constant data transmission, non-stop, assume that kind of system. So the utility modeling, we started with some kind of abstract model. We have some prior studies, assume some mathematical characteristics without actually having any physical interpretation. Then we try to improve that to come up with a utility model which has a physical meaning, such as beats per joule. And also we try to improve the utility model, make it better behaved. So first we have an efficiency function we call. Let's try to make the utility well behaved. And then there's some research from Polytech University, Virgilio. So introduced some concepts called earned throughput to power ratio, try to deal with the same problem with better results. Also from the type of system, so research is continued from the switch data to packet switch data. So packet switch data is different from circuit switch because the traffic are bursty. So it's random. Randomness is getting into the picture. So it has a statistical multiplexing. The channels are not always occupied. It's kind of shared by all the people. So also in this work, as I mentioned already, we introduced a delay requirement into the problem formulation. So in all, it's just this research focuses on utility-based uplink power control for packet switch networks with delay consideration. It's just one sentence. It's a simple summary. This is a model we use, a system reference model we use for the study. So it's just different n number of users in the system. Each user has some kind of generating packets, and with some kind of probability, we call activity probability, to generate packet. And also each source has Dmax, which is maximal average delay requirement. And different users has different locations. So H means the gain of the channel, and the different user has different power use. So it's P. All users actually the signals are interfering with each other, so it's interference system. Background noise also added there. So users are trying to transmit their packet to the base station receiver. If it's received correctly, then it's done. If not, the error packet has to go through the retransmission and go back and do retransmit until the received correctly at the base station. So this is just a basic model. So the general assumption we use is so it's a single cell interference limited network, wireless network. So with n users, and we're not considering any mobility. So user we consider stationary, and no feeding. We didn't consider any feeding. Just propagation loss is considered. And all user packets are the fixed length with m bits, with a payload of L bits. And also packet transmission are time synchronized and slotted with the interval, which is exactly the same as the duration of a packet. And the traffic, packet traffic is bursty sources. We model them as the random on-off stochastic process with the packet activity probability. And the quality of service requirement will define a maximum tolerance for average packet transmission delay, which include both transmission and retransmission. And in the delay consideration, we just consider the transmission delay, not queuing delay. So queuing delay is not in the picture. Okay, this is the second part of the talk. So this will come to the point of modeling of the utility for packet switched wireless networks. So we actually, based on our study on the utility definition for circuit switched data, so we use that as a base and develop packet switched utility. And the original circuit switch data utility has some drawbacks, some problems, and some research has been done to improve that utility. Let's say the work done by Virgilio. So try to resolve the zero problem issue. Use called earned throughput power ratio. Try to solve that. Well, I will show that later. And for utility modeling for packet switched data, so we consider the first the packet value and energy cost, and also there's two issues in the same as the packet switch system has two issues also during the utility modeling. So also has zero power issue. Then we use the Virgilio's approach, and also other one is the uncertainty issue because of the traffic burstiness. So the utility, it's a random quantity. So we have to use some kind of statistical approach to evaluate the utility. So there are some difficulties in evaluating the expected packet data utility, and we'll show next. So this is some details of the formulas of what I just talked. So for the circuit data utility, this is what we had before as a base for our research. So utility is defined as has a function here. We call it the efficiency function, FE. E stands for efficiency function. And the gamma, the capital gamma, the big gamma, it's the signal-to interference ratio. And the efficiency function is defined this way. So it looks similar to the packet success rate, but with a number 2 here. The reason to have number 2 there is just try to resolve that zero power problem. So utility here is you have a quantity similar to packet success rate, and you have the rate of channel, and you have the payload number of bits of payload, and the number of bits in the packet M. So without power here, without R and P here, actually it's just useful information bits you try to push through the channel. And with R it's a rate of channel, right? Inverse, actually it's if you put R inverse down the bottom, so it's just the bit interval. The bit interval times power, transmit power, is just energy. So actually it's the utility, the meaning is utility, is bits per joule. And the bits here is just the information, useful information you push through, not the overhead. So the ratio between L and M. M is whole packet size. L is just the payload size. So this is the concept of the utility. Then we have the PI as the transmit power for user I, and this P minus I means all the transmitted powers from other users, because those other users are also transmitting, so that those powers become interference to this current user I. Come back to the earned throughput to power ratio, and this is a concept formula established to resolve the zero power issue, because the signal to SIR signal to interface ratio gamma I. If you look at the gamma I, when gamma I is 0, right? When transmitted power is 0, then this is packet success rate. So the gamma I is also 0. So you get into a 0 over 0 situation, then it try to resolve the zero power issue. But for the efficient function we used before, it's kind of modified the packet success rate with this number 2 there. Yeah, packet success rate without this number 2. Put number 2 there. It's just try to make when transmitted power goes to 0, then this quantity goes to 0 too. Yeah. If you remember, if this bit error rate when signal to interface ratio is 0, then actually it's it has if you look at the FST, it has 1 over 2 there, right? So it's actually 1 over 2. When the gamma is 0, this is 1 over 2. So if without this 2, then this quantity will not be 0 when power when choosing. If this quantity is not 0, then when the transmitted power is 0, and this utility becomes unbounded. So that's a problem of the zero power problem. So this is a way to just normalize the success rate to correct this zero power issue. And for this is from circuit side utility we have those development. From packet data utility formulation, we're looking at the exactly the packet success rate, F gamma I. So now here we use different gammas, small gamma I. We try to differentiate from the capital gamma I. Because in the packet data network, burstiness of the traffic introduces randomness there. So we want to differentiate from the circuit system. And the gamma I, we have this expression. This is a well-known CDMA formula. So we kind of use the concrete CDMA example to formulate some of the studies. So this is W is the channel bandwidth, R is the channel rate. So this is the ratio is processing gain. And for packet switch system, we have this Xi got introduced there, which we'll call is the activity random variable. So the Xj just becomes 1 when the packet with some probability, with probability rho j, it becomes 1, this random variable. And with the 1 minus rho j, the other way, then it becomes 0.
We spent a lot of time talking about the utility functional structure of it. I guess on top of this, what I'm curious about is none of these are written in stone. The utility is just a construct, and you're trying to use this analytic construct to see if you can do resource provisioning appropriately. So why are we spending a lot of time understanding for example, the zero power problem? I would look at that as that's a rotten utility measure, except if it tells us something analytic. guess I'm missing why we're spending a lot of time worrying about the utility function.
Yeah, because utility function becomes one of the major measures in the study. So.
Not that. I'm asking kind of maybe a higher level question, maybe it's a lower level question. I'm not sure which. Utility is a construct.
Yeah.
I mean, in economics, even it's a construct.
Yep.
So
Yeah.
if it's, I don't think you're going to try to say that this utility function mirrors some actual reality.
Actually, we're trying to do that.
Well, okay, then what reality does it mirror?
Mirrors the information throughput you push through with your energy, battery energy.
Essentially, they put a battery in a portable device, and I count the number of bits I can upload.
That I like.
And so the battery bank. So it's a construct. I don't know how else you're.
That's a clean construct. I guess I'm looking at
That's
this.
what it says.
But I guess what I'm worried about is I wouldn't. If that's physical construct, then that first one, this one does not. Well, it's bits per joule certainly, but apparently it's misbehaved as T goes to 0. I don't know whether that's a problem because if your utility is you want to get a certain number of bits per joule. If you get a millibit per microjoule, that might be great.
Yeah, right. But here's the problem. You have a CRC rectification and the number of packets that get through this undetected is really many. However, the utility function, if you just say naively what you're going to do for the utility function, the math will tell you the best thing to do is use 0 power and wait for infinity, because every 6 weeks you're going to get a packet through. And by the way, I told you it's wrong. But every now and then you'll just guess. If you have a 100-bit thing,
No, I understand. I do understand. So what you're trying to do with the second bit is put a final frame on it. So it's
we move on, because that's what we want to do research about. So we don't want to spend a lot of we'd like to find out what we're doing.
So I think this is a good question. Sort of way you said it's the real bits per joule you would get in any sort of reasonable setting. If you ignore what was done to mathematically beautify this function to sort of make it analytically nice, right? And then if you sort of look at a measure like some throughput and some energy that is expended.
throughput and the like. Well, that's the standard problem because information theory is asymptotic.
So this sort of mirrors that. And so that's really the, and I don't think it's really about the
Good.
Okay, so let me continue. So it's so basically the borrow the basic formulation from the circuit research to the packet data utility formulation. Then next we'll see what's new with the packet switch system. So we define a packet value, and here is what definition is. So there's a delay here, D max there. If the packet gets transmitted and received correctly, and the packet value will be L bits, the payload bits. So you got that packet before the deadline, and that's with some probability. Otherwise, if it arrived late, then the value becomes 0. So this is just defined this way. And energy cost to push packets through, we have TP is the packet time interval, and PI is transmit power, and K is the number of transmissions you use to push that packet through. Yeah.
The way it's written, because like you write, you get L bits of value, DI is less than maximum delay. Probability that DI is less than the maximum delay.
Okay.
DI is less than the maximum delay always with exactly that probability. That's my point.
Oh, okay.
What you're saying is
I think
is it that
should without this thing.
is it that the value of a particular packet in a sequence is given L bits of credit if the probability of delay in a packet is below some particular threshold?
Yeah.
The probability of unique delay? Isn't that, reading the thesis, I don't think you're saying that, the L bits you get the value of L bits when DI is less than Dmax, and some packets arrive on time and have value, and some packets don't arrive late and don't have value?
I think the definition actually is this part, I think. The probability when the delay is less than the threshold, the probability with that probability, this event happens.
So is it correct that like you have an arbitrary packet, right?
Mm-hmm.
And now there's some probability that packet will arrive with delay less than Dmax.
Yeah.
Right?
Yeah.
Right, I think it's simpler than that. Unless I misunderstand, but I think it's a shorthand. You're saying the packet value is a random variable.
In fact, it's bad notation.
Yeah, it's bad
But,
notation.
I didn't want
It's
to
a
make this comment.
It's a random variable, and it either has value L or value 0.
This
And
is
the
sort of a-
probability that it has value L is the probability that PI
This is an example of
is.
Great, so
Is it a random variable?
Sorry.
It's not the way the thesis seems to say it, though. We will come back and look at the thesis.
So probability mass function.
I think it would be a probability mass function.
So, but this is actually just a statement of the definition of the random variable packet value. And you're saying it's L if DI is less than D.
That's how I read it.
Do you agree?
Yeah.
But it's notation.
Okay. So basically, here's the probability of that should
Should
be
be
crossed
crossed out.
Yeah.
In fact, I got this slice from him this morning at 10 o'clock. And I couldn't do anything.
No, but it's
But it's exactly that.
It's the same as
It is a random variable, right? And so when you look at the average value, then you average with respect to that probability mass function, or whatever it is. All right, go on.
Okay. Okay. I'll come back. Think about this. Yeah. Okay. So any cost is just k is number of transmissions to push that packet through. So k is the binomial distributed. So it's if it's not successful, it's just keep trying until it is successful, until the transmission is good. So the packet utility definition conditioned on the gamma I. Gamma I is random variable. So conditioned on that as signal to interface ratio, then we define this the expected value of the expected packet value over the expected energy cost. So we using the information there, so we arrive with this equation, which is still random because the gamma I is a random variable.
How come in this things you don't have condition on the arrival rate? Packets of each.
What? Can you repeat? Sorry.
How come you don't have the dependence on the arrival rates for each user?
What rate?
The arrival rates, the row, it does not depend on row.
Rho was the activity rate.
Yeah.
Oh, activity Activity is inside gamma. It's gamma's inside gamma's definition. Yeah, the gamma, it's you have the gamma is SIR. It's a signal to interference ratio, gamma I. Inside that's the activity parameter there. So it's inside there. Okay. Okay.
If user, for example, if two users want to run, do they simultaneously transfer or they resolve some collision?
This is a packet system. It's random. It's coming randomly. There's no end users there. Some are transmitting, some are not transmitting. It's just random on and off.
When two users transfer, do they simultaneously transfer at all?
This is one of the scenario. Two comes on same time, or either is on or both are off.
Oh.
Yeah, different scenario of the. Okay. So upwise equation is just a special case when the delay maximum delay tolerance parameter equals tends to infinity, then the whole formulation actually come back to the circuit data utility format. Okay, now we want to resolve the zero power issue, so we replace this packet success rate over power with the end throughput to power ratio, so to resolve the zero power. So so the final definition of the utility, because we have to remove the randomness of in the utility, which is reside in the gamma I. So we take the expectation with respect to the gamma. So we call it expected packet data utility. So expectation is taking over this part, and then arrives in this part because other things are fixed. So this is the final definition of the expected utility function. Okay. So from that definition, it's actually it becomes very complicated if you want to analyze it. Analyze it is pretty hard. It's mathematically not intractable. So what we're doing is we're trying to use some approximation method. Try to approximate one side is the interference, and another quantity is the packet success rate. We try to approximate them, so to reduce the problem to tractable format. So what we're doing is just 4 parts in this section. So first one is we need to transform the event from delay requirement to interference requirement. We'll show later, show in the following. And also the one approximation we're using is just use the Gaussian approximation method to approximate the interference. Because in packet switch system, we will normally assume there's a large number of users, each user with a small probability of being active. So this packet switch system normally we assume that way. So it's fit into this approximation method. And the packet success rate, we're using a method introduced by Jack Hausman. To reduce that expected packet success rate to some simpler formula. So finally, we'll comparison what's the difference between the exact calculation versus the approximated results. Okay, so from the delay event DI, the delay, less than a deadline. So we can, which is equivalent to signal to interference ratio gamma, larger than a gamma min, and also it's also equivalent to the total interference yi, capital Yi, less than a interference threshold bi. So the total interference it's expressed this way. So we have so all other users' power coming to the receiver, base station receiver, and with the packet activity here. So this is a random number, as random quantity with background noise there. So the Bi is the interference threshold parameter, which is expressed this way. So from the delay requirement becomes the interference requirement, and the interference requirement we can use the normal distribution or Gaussian distribution to approximate it. So graphically, if you draw the picture, so it has the distribution of the total interference to the user I. So the interference has some mean, which is mu yi, and there's some threshold there. So the probability of total interference less than the threshold is just the area under this curve.
HIs are known as the constants?
Sorry? HI.
Those are known as the constants? That's not right?
HI is the current user. It's the user you are considering.
Does an user know that value HI is not random?
HI?
Does the user know the channel from the transmitter to the base station?
User, I don't think user knows. At the receiver, at base station receiver, this is you're standing at the receiver at the base station. You try to receive the user I signal, and at the same time you have all other users come in as interference, right? And also background noise.
So the receiver knows the value H.
What value H?
Does the receiver know the value H?
Value H. A value is assumed. We should assume it is not unknown, because we assume it's user are stationary. So this pass losses we assume no, it's a fixed number.
I'll ask this question again. Do the transmitters need to know the H's?
Transmitter, no. Transmitter, I think, no. Wait.
What do they need to know to know how much power they transmit?
Yeah.
What do they need to know?
Oh, the power to, what power to transmit?
Yeah, how do they know?
Oh, then they have to know. They have to know, because this HI, HJ comes into the picture. So the total interference and its own path loss. Yeah. Yeah, it has to be. Okay, next one. Yeah, this is just the modeling, to reduce the modeling to something. Then we come to the power control part.
So what's happening here, though, is that the power control is going to change the PIs and PJs.
Yeah,
Right?
yeah.
But once, say if it settles down to some PI and PJs, the XIs, XJs will keep changing as, for newly processes for which transmitters are actually transmitting.
We actually we didn't relate them together.
No, they're not related. But if somehow the power control settles down, that the powers converge to something,
Yeah.
then the interference keeps changing based on the
Activity.
random variables, the XIs. Is that
Yeah.
right?
Yes. Yeah.
Okay.
But the final we're considering average actually is
But
just
the powers are chosen not based on the
But the powers are
Yeah.
chosen in a way that doesn't depend on any specific value.
yeah. Yes. So final result is average results actually.
Okay.
Can you not just fix the powers and just play around with the XIs to achieve what you want, achieve the utility you want to achieve?
So your XIs are they just for newly processed?
XI, right? Activity, right?
It's 0, 1 time slot independent of everything else.
Yes.
With some probability for each.
Yeah. Yes. Yeah. Assume some probability.
It's really the opposite of what your thesis does.
Yeah, but I'm just asking, can you not just play around with the exercise?
This is an uplink.
You know, you're stuck with whatever, everyone is just transmitting packets at random. So it's kind of out of control.
So sometimes randomly with a lot of.
So this is not a scheduling, this is an uplink. There are mobiles whatever, users, fixed users, wherever they are. And they have a certain activity depending on when packets show up.
Yeah, whenever they get a packet, they transmit it, and it's under control of this random variable.
Right?
It's just exogenous.
And then these models assume some form of capture because it says even though multiple transmissions may happen at the same time, as long as you meet some requirement, you get to the certain situation.
No, so he has that in his model.
Who?
Change. Like so change
Yeah.
rate is you fix your powers and then you fiddle around with those activities that you
Yeah,
has
yeah.
scheduled.
The scheduling. Yeah.
He lives with completely random Bernoulli schedules, right? So it's not his powers
Okay.
optimized.
Yeah, so in his case he cannot control it.
Oh,
Okay. It's kind of individual users'
Control
action.
powers
Yeah.
based on
Yeah.
averages.
Yeah. Yeah. Okay. The second approach we use is Hausmann's formula. So Hausmann's formula says if you have a function, let's say yi is random variable, the function of that random variable, then if you want to find the expectation of q function of q expectation, then that's a way to do it. It's just use the mean and the variance of the yi to do it. So this is a formula to do the when you try to find the function of random variable, try to find the expectation of that function of the random variable. So you say the qi inside qi is the mean of the random variable, and mean plus square root 3 times the standard deviation of the random variable, and another term is minus here. So this one, Jack Hausmann has papers report has very good accuracy to describe the average value of the function of random variable.
That's a key function tail.
No, that's a bad notation again. It's some function f. Has nothing to do with q.
Oh no, not that cute. Nothing there.
why is any random variable from
Huh?
why any random variable or not any random variable?
The anti-random variable, yes.
Q is not the Q function?
No, not Q function. Sorry.
I think it has, yeah, bad notation. It's just some function f.
same sentence as false.
Some function. Just
Some functions, you basically said if you have a function of a random variable and you want to approximate it around its mean, then you say use essentially a Taylor series approximation and use the first terms. That's sort of where it comes from.
Yeah.
And then you try to choose the perturbation such that you try to minimize some metric, and the metric that you minimize makes the perturbation such that it's relative to the mean and the standard deviation. This is part of Jack's original paper, which had nothing to do with it.
And so there's nothing in that expression that's Gaussian?
No, if it's Gaussian, it works really well. It works really well.
If it's Gaussian, it's fine. I think.
That is an approximation. His paper, in fact, was a paper published in Transactional Control. Yeah, it's a control paper that says how do you approximate a function.
They use that for the big tail analysis.
But it is one of the most
Yeah.
famous approximations
yeah.
that is being used. It's not in textbooks. It's in any kind of CDMA analysis you see in a textbook. This is one of the approximations here. They say the central limit theorem, then there is coefficients.
Yes, sir. Yeah. Okay.
Anyway, yeah. Oh, it has nothing to do with you.
And nothing. Okay. Q is just any function, not the Q function. So use this formula, we can try to find the expected packet success rate So there's three terms. By using the total interferences mean and standard deviation. So this way simplifies the analysis.
Get over. Go ahead.
Okay. Okay, this is just a picture to show the utility function, utility function as a versus the transmit power for some three different activity probability. So you have this kind of curve with a single peak, and going up and it's going down. So, sorry. For this one, I think it's 20 users in the system in the parameter we assumed.
So do you have a comparison of some maybe for N? I think we talked about
Yeah. Next one.
All the users have a symmetric activity. They're all for any
Yeah,
flow,
for this.
everyone uses flow.
For this one.
What about the power each person uses? Is each person when you say the power of the UI is 3, does that mean all the users are using power 3?
Oh no, this is for user I, the power.
So in this graph are hidden all the powers of the other users?
Yeah. For this plotting, it's just assume total interference is fixed, so you plot the same, just to see the shape trending, not any real thing here.
So
If fixed total,
really have the interference. It's just
just assume some number there. Yeah.
okay.
Then the number of users doesn't matter.
Yeah. For this plotting doesn't matter. Yeah. It's just show the shape of the
Because
utility.
you're trying to do utility-based power control, right? So just trying to understand how in your own variable your utility works.
So next one is just comparison of the exact calculation and the one user approximation. So you see two curves here. One red one is the exact method, and this is a special case with 5 users. Because because larger, the exact calculation becomes very complicated. So I use a 5 user system, and for the blue one, dotted blue one, is the approximated results.
So you just use some numerical routine to figure out the exact one. Is that what you're doing?
Yeah, numerical calculation to get that, I think. Yeah.
So what about the other users' interference in this?
For this one, what we did is assume they are all the same at some location, fixed location.
Like all the other users have some same power?
Say, all for these two cases, right? They're all the same
If they're
system.
same or not, it's fixed.
Yeah. I think this is the curve that corresponds to the thesis, right? You wrote this expansion for, there's 4.
Yeah, this is 5 user.
16 terms.
Yeah, there's a lot of terms.
Right, and then this is the comparison of the exact expression
To the-
approximation.
Yeah, approximation. Yeah, I plotted them here, so you can
But
see.
in that, then all the interfering users have the same power and the same activity.
There's
It doesn't matter. I mean,
Well, it matters to the exact thing.
No, but here's the thing, right? The reason why he's saying it doesn't matter, he's right, is that you're trying to essentially study the properties of your utility function, because when you do a non-cooperative game, remember it's Pi and P, that notation P minus I, basically you're just trying to study the concavity or the quasi-concavity of your own, of the function in your own
Whatever
variable.
powers the other users have,
Yeah.
right?
Right,
So
right,
you
right.
introduce some
So
distribution on the interference of each time, and will give a slightly different curve for the
Yeah,
exact.
yeah.
So I'm just trying to pin down.
Yeah, so the question is whether, I think the
Yeah.
answer is, suppose you change the interference to some other level, would you still have a kind of a match like this?
That's kind of
it should have the match because I assume all those things are same, right? For approximate one and the exact calculation one. They're all the same.
I asked that question about this because I thought I understood this one from the thesis. I only really asked because the last one, which I thought, based on remembering this one, it turned out to be not what it said it was. It turned out to be all we took a constant difference. That just, so I thought I would ask. And so this is what he says it is. Or at least
So no, but in computing that exact expression, right?
Okay.
You had to assume some distribution of the interferers.
I think there's 5 of them, and they're on each with probably
0.5, yeah,
0.5,
okay.
and they have some fixed power.
Yeah. So all other users are fixed power, I think. Yeah. What just try to plot the user I's power and put the user I's utility in 2 different ways. One is exact, one is approximated. Okay. So next part is about the formulation of and the solution of the game-based uplink power control problem. So here we come to the power control part. So we use a non-cooperative gain and distributed power control formulation for formulate the problem, and we're trying to find the solution to the problem, and we need to prove the Cauchy concavity of the expected packet data utility function. We did some analysis there, and we have to prove the existence and uniqueness of the solution. The solution of the game is a Nash equilibrium solution. Okay, then the final one is how to compute that solution. Use some method to compute it.
I just have a question.
Okay.
Why does the utility look very peaky in the regime where the transfer power is very less?
When picky, right? Here, I mean, because the power is at the bottom, and the packet success.
A lot of utility when you transfer that very less, but that should really depend on your where you are located in the geography. I mean,
Oh, of course. Different location have different utility shape. Yeah. Why picking here? Because the transfer power is at the bottom of your utility. So when transfer power is low, the utility is high.
then it should be reached at when it is just above zero.
That's what he explained in the beginning. It took a long time to say that if you went to the exact formula, like we said, if you didn't fix this, then what you would have is exactly what David said. The optimal thing is to basically not transmit at all.
Don't transmit at all and just guess.
Just keep
And
guessing.
every now and then you get the correct path.
Keep guessing. That's what maximizes bit
So
control.
0 power, so you have infinite
See, the
utility.
problem is bit error rate. The worst case bit error rate is not 1. It's a half. It just corresponds to that.
Yeah. Okay. Thanks. Okay. No. Of the game, we just have.
Sorry, I have one more. So does it go at asymptotically saturate at some? Does the utility asymptotically saturate if you keep putting infinite power into your system?
It really depends on the interference where you have one.
No, but the interference will saturate at some point, right? Because if everybody transferred at infinite power, let's say.
Infinite power?
Zero utility.
You don't have any utility.
Because
Interference.
power is in the denominator.
Oh, yeah,
Mathematically.
it's per joule.
Yeah.
So if they transmit with not enough power, they're making too many errors, and they don't get any utility. If they transmit with too much power,
So ultimately it should come and go down to
To
zero.
zero.
that's
To
what
zero.
it's shown, I think. Wait.
Must go.
That's fine.
Has to go. Yeah, has to go there. Okay, it's just some notation. For a game, you have a utility as a matrix, and the SI is the strategy space, and N is number of users play the game. So for formulate the power control problem, then it's just every individual user, let's say user I, try to maximize its own utility. All the users in the system do that. So it's kind of non-cooperative. So nobody care about the other people. Just try to maximize your own utility. So the solution to the non-cooperative game is called Nash equilibrium solution. So the Nash equilibrium solution is just describe a situation, describe an equilibrium point where in the system becomes at an equilibrium. Any user you want to change your power, transmit power, it just hurt the system, hurt yourself. So you unilaterally change your own power will not give you any benefit. So all the users are like that in that situation. So the system will come to the equilibrium point. That's the solution point. So for a Nash equilibrium solution, the first order condition for it just takes the first derivative of the utility function with respect to the transmit power for all the users in the system. And this will give you the condition for existence of Nash equilibrium. It's just a necessary condition. Okay, so for the utility function we have, actually, we have the expected utility. Actually, we have two main parts. This is a constant. And we have first part is expected packet success rate over power. And another part is probability, delay requirement. So we to prove this utility as quasi-concave in order to prove the existence of Nash equilibrium. So there's a theorem in some of the lecture notes from NYU, I think. So it's, the theorem just says if you have two functions, psi and phi, and then if you put two functions together, compose it together, then so if one function is quasi-concave and the other function is non-decreasing, then the phi composed with psi is also quasi-concave. And if psi is strictly quasi-concave, then and phi is strictly increasing, then the result will be strictly quasi-concave. So we'll try to show our utility function have that kind of behavior. So the result we have is A part, this part, it's a strictly quasi-concave function of transmitted power. And the second part is the probability, which is strictly monotonically increasing function of transmitted power. So actually, the total results is strictly quasi-concave function. The detailed proof is in the thesis. This is some of the propositions and corollaries used in the proof of the Nash equilibrium solution. And this one is a very famous theorem by Debreu. So it just says Nash equilibrium exists for cooperative game in which if each user's utility is quasi-concave in his own strategy, and if the strategy space each user is non-empty, convex, and compact. And we also proved in the appendix of the thesis to show the strategy space is non-empty, convex, and compact. Okay, then we have that first order condition. Then after some calculation, we have this equation. It's also still the first order condition. And from this equation, first order condition equation, there's a solution function come out of this, which is beta equals g of alpha. And where alpha is defined as mean of the total interference divided by the standard deviation of the interference, and beta is defined as bi as the interference threshold divided by the standard deviation of the total interference. So the solution functions come out of this first order condition. And this part which we try to get a closed solution, closed form for the transmit power. So we have this expression with G, this solution function here, and this part is alpha. And we use some first order polynomial curve fitting method, and find out the relationship between alpha and beta. It's almost linear. So beta is interference threshold divided by the standard deviation of interference, the total interference. It's normalized up. Okay. So because of this approximation, so we can express transmit power into two parts. One part is mean of the interference, and plus standard deviation part of the interference, with two parameters constant. The constant is coming from those curves, those approximation curves. Not curves, lines. One is the slope, one is the shift. Yeah. Okay.
So you, PIs, you feedback those numbers from the receiver to the transmitter to get the. Is there a feedback? Because it seems that you need to get this.
You mean there's two numbers?
YI is the total interference you see due to each user transmission.
You mean which number?
YI.
YI? YI is total interference.
So the total interference is only at the receiver you know the interference.
Yes. Yeah.
So you have to feedback that numbers to the transmitter so that they adjust their powers.
Yeah. From here. Yeah. Yes. Yeah. Because you have to know the mean of the total interference and the standard deviation of the interference in order to get your optimal transmit power. So this information has to come from.
Distributed, you mean each user independently does? What do you mean by distributed? When you said some distributed power control, what do you mean by that?
Distributed is just because every user is doing independently. This is at the equilibrium. At the final solution point, you have these results. This is your results, your optimum power you use. After calculation, got these results, which depends on this thing. Yeah. That's a good question. Okay, so this part is about yeah.
So are you planning to show all the 56 slides?
I have skipped some of them.
Okay, so I just want to make sure that you're sort of aware of time.
Okay, I'll speed up.
Yeah, so you need to pace yourself and maybe highlight some of the results.
Okay.
Try to tell us what's the important things that you've actually done.
I think so far you set up the basics of what
Yeah.
So I think your utility has all these nice properties.
Okay.
Right? And you're able to show existence and uniqueness of your Nash utility, all that I think you established so far.
Sure.
Now I think you focus on sort of highlighting.
Some of the results. Sure. Okay.
Yeah.
Okay. Sure. Okay. For some of the characteristics of utility function, utility-based power kind of strategy. So this part will show some analytical results using that formulation, that's closed formula. So one scenario is when the traffic activity for every user are the same. If I assume that, and also the packet delay requirement are all the same for the user, then we come to the conclusion that all received power at the base station are all the same, and all those parameters, interference threshold, mean of interference, standard deviation interference, all the same. They are all the same. So there's no different. At the equilibrium point. This is one scenario. And on this all equal scenario, we can compute capacity of the CDMA, which is we assumed as an example in analysis. So we can get a formula for the capacity of the CDMA system for the switched data services, packet switched data services, and also we can get the received power at the equilibrium point. And this is a curve from plotting that capacity formula. So you see the capacity decreases with the increase of the activity. And also, if you're looking this way, and actually I have another plot. This one is capacity changes with the packet delay requirement Dmax. So it increases with Dmax. Dmax is bigger. That means you're not that tighten on your delay requirement. Then it's, capacity is bigger. Yeah, it increases with the delay requirement. And the non-scenario is we still assume equal traffic activity, but users have different packet delay requirements. And what happens? It's if that's two group of users, one group of users have a delay requirement which is different from the second group, then we still come to a Nash equilibrium, but with different received power for different type of user. And for different type of user, the expected packet success rate are different. But within the group, within the same packet delay requirement group, they are the same. And this is supported by the simulation also. Yeah. And this part we discuss about the packet switch system versus circuit switch system, because we want to try to relate this two. And the point to relate this two is that traffic activity becomes 1. So you're not on or off, you're always on. Then the two systems are equal. So when rho equals 1, so this randomness is going away, and standard deviation becomes 0. So all the formulation going back to the circuit formulation, and the probability of delay requirement becomes 1.
So you made a row approaches 1.
Yeah.
Right, that approaches 1. Is it
so you approach 1. Yeah.
when row equals 1 is the probability. Every packet there's never a packet in error, is there?
Rho is the activity probability. Rho is activity probability.
Yeah, so you go to everybody is active all the time.
Yes.
The interference in every slot is the same. And at that point, don't you engineer the powers? So the powers then are fixed.
Powers.
You end up with some solution to the power control to fix a fixed set of powers.
Yeah, I think for circuit switch, yeah, final at equilibrium.
And
Fixed.
then in the outcome of that, isn't it that every packet is transmitted perfectly the first time it's sent? There's no I assume that's what it is, but I'm asking you to confirm it.
Transmission is still, retransmission is still there, I think.
Wow.
This is a continuous going.
The noise is just at DC levels. You don't actually have any real noise, right? You just have the noise power as an additional term in the interference.
Yeah, but the threshold will be different for different types.
What threshold?
He has a SNR detection threshold for each user, and if somebody goes below that threshold, it will be always.
Let's let the defendant here.
I think interference is still there, right?
Well, it's just a number, the interference power.
Yeah, but that number would determine your packet success rate, right? This here has a packet success rate as a number.
So you're saying, okay, so you say, oh, you get a fixed SIR.
Yeah.
SIR.
Yes.
And you're saying that fixed SIR determines a packet, a frame success,
Yes.
which is still less than 1.
Yes, correct.
So why do you say that it approaches 1? Why isn't it just that all these frame success rates are, so for a given frame success rate, right?
Mm-hmm.
That's going to be fixed. There's some probability your delay is less than the threshold.
You mean this one, right?
I guess I think that either there's sort of two possibilities. Either limit rho goes to 1 of that thing will equal 1, like on the left-hand side, right? Or it equals some number not equal to 1. But I think the limit is, it exists, and this on the right-hand thing say it approaches 1. I think it's not true.
I think it should be equal to 1.
Yeah,
I have a feeling the gamma star that you got is a D-max account. So I have a feeling it will make sure that it shows up as the linear requirement of it.
Yeah, with the gamma star, you're always aiming for a certain frame success rate.
Right.
So if you have some
So if you have some that are in error,
there's some very small,
not even that small.
geometric
Oh, it's some number.
it's not even that small.
There's some geometric tail.
No, you're right, it's some
that
number
You don't
actually.
need, you
Yeah.
have enough.
It's not 1.
That's not correct, yeah.
Not 1, it's some number.
Definitely not correct.
Unless you're saying something else.
Well, yeah.
Right?
Well, yeah, I mean, Roy gave him another alternative. And you said, well, when you do stuff, it's not an
Yeah. Okay. So I think I agree with you that you end up with some frame success rate, and then there's some
probability, of having infinite delay.
enough
Yeah.
misses at that frame error probability.
Yeah.
Okay. Let's keep going.
Okay.
The delay is geometric.
Right.
So the frame of error once it's always been error because the interference is the same. Even for
Yes.
transmissions.
Right, or it always is that it's never an error, right?
Yeah.
Depending on what the, but in fact, right, he has some practical thing. It is some number. Okay.
Okay. Okay. Next part is just a simulation studies to run a simulation and to check different scenarios here. So it's let's see. One scenario is to see the traffic burstiness, that's activity probability, the effect, and equilibrium, the signal-to interface ratio at equilibrium, also transmit powers and utilities at equilibrium. And next one is to see the delay tolerance parameter and those SIR, transmit power, and utility effect. And also how about the user distance and those transmit powers and utilities. And also last one is when it's unequal delay tolerance parameter, delay requirement is not equal in the system, then what effects on the power control solution. And finally, we'll also compare what we got from analysis and the simulation to see if they are matching. Sorry. Yes, you come to that. Yeah, it's at the final solution point. Okay, this shows the equivalent SIR versus activity probability rho. So it increases with the activity. So the activity more, you need a higher SIR to run the system. And this shows the transmit power this side and the utilities on this side. And the top graphs are showing the 20 user scenario. 20 user scenario, and the lower two shows the 10 user scenario. 10 users, so 20 users, you had activity to some point, it's approach the capacity, you cannot, it will just shoot up. Yeah. And this is the effective delay tolerance on those SIR, transient power, and the utilities. And it's when the delay increases, the SIRs actually drops. Sure.
Simulations to adjust the powers, you measure the mean and variance receiver. So that mean and variance over what window do you measure?
In simulations, actually each iteration, one iteration, everyone is adjust their power, right? Then the next iteration, the interference changes. Then they have to, everyone is adjust.
Oh, okay.
Iteration by iteration. Then finally, they're not adjusting anymore. Everyone stays the same. Then we come to the equilibrium point.
Well, if you had a continuous real-time simulation, let's say, then
Real time.
not this simulation is like a snapshot, and then you
Yeah, snapshot, and each iteration just like that a snapshot, I think.
Yeah, I'm trying to see how to implement it. If you had to implement it in a real situation, so how do you measure the interference?
Just like a slot by slot. Yeah. The slot you have some results, then next slot you adjust.
Okay.
And come to some kind of equilibrium point.
I think you have to go to some kind of a two-level scheme, like how sort of, you look at Qualcomm's power control, right? Or a circuit switch, what is system? Even for that simple SIR balancing, the way they sort of implemented this sort of has a few attributes and immunities that basically does some fine measurements and then sort of a slower. So you have to do something like that, because otherwise there is too much variability for you to measure. I think you're sort of asking that.
Yeah.
Yeah, so no.
How do you do?
You have to go to an approach like that, where you do like an inner loop that does sort of fine updates, right? Where you say you're either raised up or lowered by some fixed number, delta dB. And then you adjust the target from outside. So you have to go to something like that here also.
I will have a window after
Right. Because, what trying to get a feel for what size the window should be. So, anyway, so offshoot.
Thanks.
Yeah, but here it's
Vibration.
just activity, so you should be able to get a gauge on it. It's just the only thing changing here is the on-off activity of something.
Okay, I'm going to quickly skip some of the plots. So if you're interested in synthesis, you find them. So this is a distance-wise. If all users are on those distance, then for different activity, then you have different equilibrium signal to interface ratio at equilibrium. And this is distance-wise also. So the far user has to use a higher power, and results in a low utility. Equivalent SIR, right? Signal to interface ratio.
So the SIR
Insensitive, yeah.
I think one of the basic things of this whole thing is everyone should aim for the same SIR.
yeah, right.
So that's all it says. Right.
only
That's the Nash equilibrium, everyone ends up with the same SIR. So that's all it says.
Well, but so is that
So does everyone have the same activity probability? Like in the system?
Yes. For this case, it's all the same. For this case, all the same. For this case,
So probably at the higher distances, there should have more power.
So suppose
Yes.
you create a population where half of the people use activity 0.1 and the other half use activity 0.4.
I did that for different delay requirement. That's some results on that. Well,
They were already simulation results.
okay, so this one. This one is with unequal delay tolerance. So I have a group of people. Say this red one is all the people has 2, Dmax has 2, and the blue one is all the users has a delay 5. But for green one, it's half of them. It's half of them is 2. Delay is 2, and half of them is 5. So you say the SIR are different. There's 2 groups. What?
The ordinate. The vertical axis or the units?
Oh, this is absolute value. It's value. It's just a number.
The thing is, this range of numbers is not so far from the dBs.
Yeah.
Like 5 dB
Oh,
is like 7.
7 dB is 5.
7 dB is 5, right?
Okay. Yeah. So this is SIR. If you look at this is a transmit powers. If you look at the green one, it's have some. It's not all the way, but it's just first group, the second group. So there's some crank here, and also the utilities is here. That's a little bit changed. So the green one has 2 groups. Yeah. And the others just some example. If one user tightens its delay requirement, what the effects of on the system, and or one of the users if relax the delay requirement, what the effects on the system. So those are examples. Let me just go through quickly. So this plot is just compare the analytical results, which is red one, and the simulation results, which is blue one. So that's not exactly match. And the reason for that is because in analysis we actually use the extra approximation. If you remember that A0, A1, the linear approximation of the solution function, that part may introduce some of the extra errors there. Because for simulation, it's that part of approximation is not there for simulation. But for analysis, we use that extra step to make a closed form solution, closed form expressions. But the tendency is the same. Okay, this part, number 7, we just extend what we did into a multi-type traffic scenario.
Was he supported on that multimodal?
Yeah.
Right.
Yes.
Okay.
So I
Started with
I'm
that.
sorry.
yeah. So
I was thinking I could see that word in a few years.
I'm just going to be Jim Flanagan.
Okay, so just 2 types of traffic we assume. Let's say one is the traffic V with a tight delay requirement. Another one is D with a more relaxed delay requirement. So there's 2 types. We can formulate them all together. Use that formulation, and this is some of the results. So let's come to this section 8. It's about the performance analysis of the proposal scheme. So we have this power control scheme, but we don't know how it performs. So what we did is we create some idealized slot-by-slot power control schemes. But by slot means we mean at each slot the users are getting all the feedbacks from base stations instantly. So every slot user has exact perfect information about the system, the number of users on the channel, and interference, everything. So in that case, the slot-by-slot power control should be doing perfectly, the best, the best, right? Best way to do it. Then we can compare our scheme to this idealized scheme to say, are they far from each other or are they close? So to design this slot-by-slot strategy, we use these two strategies. One is called network-assisted power control. This is also the work from Dr. Menden. So we use that power control strategy applied to slot-by-slot basis. And also the other one, we also consider the distributed power control strategy, which is the strategy we use for the circuit switch data utility circuit switch data scenario, and we put in a slot-by-slot basis. Then we put our scheme into the same situation, slot-by-slot. Then we compare the results. So this is just a picture to show what do we mean by slot-by-slot. So our strategy is kind of our strategy is responded to the average interference in the system. But slot-by-slot, we mean that every slot because the information is interference is different. Number of active packets are different. So the slot-by-slot strategies react very quickly to find the best power to use to transmit. Okay, this is just the source where we got these two schemes, and the whole scheme we call it a average distributed power control, and the results we compare is like this. This is for 10 user scenario. So for the slot-by-slot network assisted power control, we have the red one, and for the slot-by-slot DPC, distributed power control, is green one. And the blue one is what we proposed. So from 10 user scenario, it is very close to that slot-by-slot distributed power control performance. So the network assisted power control slot-by-slot is always has a better. This is utility. The higher, the better. And this one is plotting the 20 user scenario. So you can see this is blue one is our strategy. So it's very close to the one which is slot-by-slot distributed power control scenario. Okay, this is a performance comparison with other schemes. Okay, then the conclusion we make here is first one is we use the several approximation methods and techniques to try to reduce complex and intractable power control problem into a tractable form, and studied analytically and by simulation. This is the first point we make. And also the second point is so the proposed power control scheme then the behavior is to allocate the power according to the location of the user and the delay requirement and also activity of the packet traffic and also the total number of users in the system. And this total number of users system is the real number, how many users there. We don't care about who is active, who is not active. and also the mean and the variance of the total interference, and also background noise. So for the solution of the power control scheme we propose here, it has a unique Nash equilibrium, which depends on the user traffic and the packet delay requirement. And this is when identical traffic burstness of traffic activity and identical user delay requirement, they will come to a unique Nash equilibrium, or with all users have the same unique signal-to-interference ratio for all users in the system. If unequal delay requirement, we still come to a unique Nash equilibrium, but resulting in unequal SIR. And the next point is just example in the simulation where we showed that when one user in the system changes its delay requirement, what the effects on other users in the system. And another point is we showed the formulation can be extended to multi-class user traffic scenario system environment. And also performance analysis, as we just showed, it's performance achieved for each user adapted to power level to the average interference. It's not too far from the those instantaneous interference scheme adapted to the instantaneous interference on slot-by-slot basis. So in general, this work provides a new approach based on the approximation techniques for the study of the uplink power control for packet switched data system, wireless system, and study should provide some guidance on efficient management of transmitted powers for energy efficient packet switch data services in wireless networks. That's it. Any other questions, comments?